Start.
Oh, is this being recorded?
Yeah. Hello, I'm David. If you've never seen my face, then hello. You guys can see me, but the people who are watching online may never have seen me. So hello to you, and that's enough of that. This is a revision seminar for Intro to Financial Maths. It's Semester 1, 2019, and I've been given some requests, and we'll do our best based on my uni lecture notes being difficult to decipher what is where, and I'll see what I can do. You guys who are here, it is always okay to, within reason, to interrupt me and ask me what I'm doing and how I decided to do what I've done, or to tell me, oh, the lecturer didn't do it like that, or any other information like that. If you think of questions that you want to talk about, say them up, and when we get to them, we can talk about them more, and I will go for about 2 hours and then I'll stop. And Maths Learning Centre is open all the way to the end of the exam period if you want to drop in and talk about anything there. Okay. Well, I will take the requests in the order I think of them. So my very first, very brave question, before anyone asked any questions at all, was inverse functions, so I'm going to start with that. So the point of an inverse function is to undo the function you were thinking of. So if you had a function that did this is just some intro ideas. So some intro ideas, if you had a function that did this, like that, then the whole point of an inverse is to go backwards the other way. So the idea is that if 1 goes to 2, and that's what f does, then f inverse comes back the other way and sends 2 back to 1. The whole point of it is it undoes whatever it is that the original function does. This -1 notation is copying the notation for the way multiplication works. When you multiply something and it's inverse, you end up with just 1. And it's extremely confusing because when I write f next to this number, I'm not multiplying it by f. I'm performing the action f upon it. But when people first started writing function notation, they were the functions they were thinking of. So that's what we're stuck with. So f inverse does not mean 1 over the function. It means the function run backwards. Okay, so that's the idea of this. And what we would like to do is if we have a function that has a formula, we would like to find a formula that comes back the other way. That if I take the answers from the first formula and put them into the second, it will go back to where the original inputs were. So the second idea is that if you have a function that where 2 different numbers end up at the same place, then you won't be able to decide what the answers for the inverse function is. So if my function is supposed to come backwards to this, if I come backwards from 2, I can either get 1 or 3, and I won't be able to decide at any moment which one it is if I weren't told where it came from. If I was just told, aha, f of something came out as 2, I won't be able to tell how to go backwards. And so I can't do an inverse function unless every input produces a different output. There is no dot over U, but I'm just getting over my... Okay, and that is called being one-to-one. So when I talk about a function being one-to-one, it means that the only... every different output has to produce every different input has to produce a different output. So the terminology for that is 1-to-1. So this function has at least 2-to-1. I've got two inputs producing one output. So it's not 1-to-1. I don't know how your lecturer defines it. There may be two definitions. One is that if you put different inputs, you get different outputs. So it could be defined as if x1 is not equal to x2, then f of x1 is not equal to f of x2. That's one way of doing it. Or it could be if f of x1 is equal to f of x2, the only way to do that is for you to put the same input in. So these are two alternative ways of defining 1-to-1. I don't think your lecturer cares which one it is, but it wouldn't be the worst thing to check what your lecture notes say. Because some lecturers, this course they're probably unlikely to ask you for definitions. Do you guys get to write a sheet of notes to take with you? Okay, so they're unlikely to ask you for definitions because you'll just be copying off your notes in this course. But in a course that doesn't have notes, they're likely to ask you definitions in an exam because they want you to remember them. So anyway, they're both the same thing. This one's a little easier to talk about. This one's usually a little easier to use in a proof. Okay, so just some ideas that go into this. You can't have a one-to-one function unless every input has a different output, or you won't be able to decide how to go backwards. And the whole point is going backwards. And what you want is a way of doing that. So let's just do an example. Let's do that. So this is my function. It's x squared minus x, but only if x is greater than 1. This may have been a bad idea, I'm sorry. I'll do it anyway, but it might turn into crap. So just pay attention, and I'll do a second example if it does. Okay, so this is an example. And if I wanted to actually do this, the first thing I would do is try and imagine what it looked like and think about what this function does. So if I start at 1, I get 1 squared minus 1, which is 0. And then 2 would give me 2 squared, which is 4, minus 2, which is 2. And then 3 would give me 3 squared, which is 9 minus 3, so I'd get 6. So different inputs seem to be giving different outputs. It may be that if I put a half one in there somewhere, it'll turn out to be something I've already got. But the person, if your lecturer asked you this question, they wouldn't actually, they would make sure it was something that did have an inverse. So what we're going to do is we're going to find a formula for h inverse of x. It doesn't matter what letter they use. Okay. Cool. Well, I'm going to imagine what the graph of that looks like to begin with, just so that I've got a clear idea of what this is. Okay. So there's 1, and my function only exists here because it says x is greater than 1. And x squared minus x. Okay, well I know that x squared would be like a parabola like that. X squared minus x would still be a parabola, but best plan would probably be to factorize it. Okay, so that's 0 when x is 0 and when x is 1. So it's going like this. One of the things that they want you to get out of this course is to know the shapes of various graphs. So they're assuming you know how to do this. And so we just want this bit here, that bit there. The rest of it we don't care about because we only want the part where x is greater than or equal to 1. So yes, it is 1-to-1. because every input produces a different output. And the way I can check that is to see if I draw a horizontal line, it never crosses it more than once, because I'm not using this bit here at all. Feel free to interrupt me or say any comments you want at any time. This is for you. You will not offend me or embarrass yourself if you ask a question, okay? Okay. Now that wasn't necessary to solve the problem, it was just getting a handle on what's going on here. Okay. So I'm going to need to figure out a formula that if I take these answers, figures out what these answers here are. So I know that my formula, when I put in 1 for x here, it produces 0 for the answer. So I need a new formula that when I put 0 in, it produces 1. When I put this number in, it produces that answer. When I put this number in, it produces that answer. Well, the traditional way of dealing with that is to just give your function a name. So what if I did this? This may not be how your lecturer does it, but this is how I do it. Oh, it's not f, it's called h. Damn it. So used to functions being called f. This is the thing that I want. I want something that produces h, I want the formula for h inverse of x. That's exactly what they've asked me for. So one way of dealing with that in maths is to give the name to the thing that you want. And so what I'm going to do is I'm going to do the only thing that I know that h inverse does is that h undoes it. So if I did this, then that would be true. So the point is that if h inverse takes x to y, then h should take y to x. Now this is the reverse of what you'd normally see. Normally you'd think of this producing y, but I'm deliberately doing it backwards because they asked me to do h inverse of x. Okay. Well, I know what h of y is. It's this, but with a y. Well, and then I need y equals. Because if I could figure out what y equals was, then that would be the correct formula for h inverse of x. Well, that's not fun. That's a quadratic equation. Okay, well let me just think what would happen if this x was a number. If I had the number like 7, then I would have y squared minus y equals 7. And if I wanted to solve y squared minus y equals 7, I would do the quadratic formula usually. And so that's what I'm going to do. I just have to put x where I would normally put that number. So y would be, let's see, minus b plus or minus b squared minus 4 times a times c, but the c is minus x, over 2 times a. So normally people call the coefficient here a, the coefficient here b, and the coefficient here c when they do a quadratic equation. I try not to write them down on the page because if there's already a's, b's and c's in my formula, it gets me really confused. So what's that? 1 squared is 1 minus 4 times minus, so that's plus 4x over 2. Okay. Cool. So that must be what h inverse of x is. Except it can't be a function if it produces two different answers. A function only produces one answer at a time. So it can't be both the plus and the minus. So I'm going to have to choose whether it should be the plus or the minus. And why do you say that? Has to be greater than or equal to. Cool. So just saying greater than or equal to 1. So you're saying that the inputs here have to be greater than or equal to 1, and the inputs of h are the outputs of h inverse. Oh, right, okay, so h inverse produces the answers, that the questions that these came from, so it has to be greater than or equal to 1. Okay, so And so we get that y is 1 plus root 1 plus 4x over 2. And I really would have liked to have fit all of that on one page, but I'm very bad at that. And so h inverse x is 1 plus square root of 1 plus 4x over 2. Let's just check if it's working correctly. When I put in 0 here for x, when I put in 0 here for x, when I put in 1 here for x, I got 0. So when I put in 0 here, I should get 1. 1 plus 4 times 0 is 1, and so 1 plus root 1 is 2. 2 divided by 2 is 1. It does produce the correct answer when I put in x equals 0. So it's matching up with what this is supposed to do. Putting 1 here produces 0, so putting 0 here should produce 1. And I know that's only one number producing the right answer, but it's a good start. Okay. I'm just going to do one more example, because there's a classic one that turns up in assignments that wouldn't be the worst to do. Something like that. Okay, so I have let f of x be x plus 1 all over 2x minus 1 for x not equal to a half. Find a formula for f inverse of x. So this function is totally going to be one-to-one. It certainly has a vertical asymptote when x is a half. So whenever the denominator is 0, there's a vertical asymptote there. And if x was very close to, if x was a little bit bigger than a half, this would be a positive number, and so I get a positive answer overall, so it's going to go up there. And if x was just a little bit less than a half, this would be a positive number here and a negative number there, so it would be negative, so it would be going down there. And I don't know what's going on in the middle. It must flatten out at some point. If x was like 1,000,001 divided by 2,000,000 minus 1 is nearly 1,000,000 minus 2 divided by 2. It goes towards a half. Okay, so if x was a really huge number, it's going to head out this way towards x equals to a half. And this one's going to be like that. Okay, something like that. It's not the best picture. So according to the way this picture works, it is one-to-one, no matter which, no two x's produce the same answer for y, so that's good. And we'll just see what happens, eh? So let's see. F inverse x, which means that f of y would have to be x. And when I sub in y into the formula, I get this. So I should point out here that some people, when they do this, they start with y equals this, and they rearrange it to get x equals, and then they put the sub in the x at the end. And that's perfectly acceptable as well. You can do either one of them. So why don't I do them both so that they're both here? So why don't I do the other one? Let me do it backwards. Okay, I'm going to do both versions so that you can see how it's done. Okay, so my goal is, I know that f inverse of y will be x, because that's how it works. So my goal is find x equals, well, solve for x. My dyslexia is not doing very well today. You'll notice that when I start writing a word, I don't always write the first letter. Okay, so let's see. I'm going to start all the way over here, if that's okay. So I want to get to x equals. The thing that's most annoying to me at the moment is the fact that there's two x's here that are on top and bottom of a fraction. That's annoying. And the fraction is the most annoying bit, so I'll get rid of that first. So what I did is I multiplied this by 2x minus 1 and multiplied this by 2x minus 1 and produced this, so at least I don't have any fractions anymore. Really annoying to have two x's, and actually it's annoying now because this x is trapped inside this bracket. I'm not going to be able to I need to get it out of that bracket in order to put it on its own. So I'm going to expand this bracket, expand that multiplication there. And at the very least, I can put all the x's on the same side. So I've subtracted x from both of these parts, and then I've added y to both parts, and that's produced this answer. Now, I need to somehow remove all of these things from the x's. I can do this. These both have an x. I can factorise that x out and leave a 2y minus 1 behind. And now I have achieved the goal of only having one x on the page in this line. So now I can divide by this. So now we know that f inverse of y is y plus 1 over 2y minus 1, which is exactly the same function as we had before. What? I did not that's rare. It is extremely rare for a function to be its own inverse. But it's the same as what we started with. I guess there's like a line of symmetry along there. Okay. Very rare for that to happen. And so the specific question at the beginning said to find f inverse of x, not f inverse of y. So I should write it with x's instead of y's. I don't know if someone in marking an exam would to remove a mark or a half for that sort of thing, but it's better to be safe than sorry. So this little move here where we clear the denominator and expand it out and then factorised again is something that if you've seen once you can go, oh yeah, that's right. But what I was trying to do is show you how I would have come up with that without being shown, which is to get rid of the fraction first, because everybody hates things being trapped inside fractions, and then everybody hates things being trapped inside brackets. There's no point dividing because that just goes back where I was. And that was the reasoning I went through to come up with that solution. I think that comprehensively covers the finding inverses question. Cool. That's a good start. Better not mix up my Algebra Pure Maths 2 notes with the IFM notes. That would be very confusing for you guys. Okay. So, what are we looking at? How about I talk about the bisection method for a little bit? Yep.
Do we need to do graph for the exam?
No idea. Sorry. So for the purposes of the recording, do we need to do graphs for the exam? I don't know. It seems to be something that's an important part of this course, being able to produce graphs. Okay, well, if none of the sample papers have graphing, then I wouldn't expect your lecturer to want you to know how to do that. But it is a useful skill to have for making decisions for what to do. So maybe not as accurate as a graph of this, but at least knowing that it's going to be roughly this sort of shape is a good idea. Okay. I'm just going to have a look at the notes about the bisection method. Okay. Cool. Okay. Do you want me to explain something?
Oh, I was just asking if the best way to recognize graphs.
Yeah, I think I actually have a video about that on the Maths Learning Centre's page for IFM. I could be wrong. But anything with a squared in it, you know, is this shape. And anything that has linear over linear, doesn't really matter what it is, but a single x here and a single x here, is always going to be one of these shapes. It always is one of those shapes. And you know that the vertical line happens when the bottom is 0, like this bit. And the horizontal line happens when x is really huge. So you pick a very large number and that should tell you where the horizontal asymptote is. That was a good thing to have for a bit. It's good to know that. There's some functions that they'd like to choose. Other than that, e to the power of x, y equals anything to the power of x, tends to be this shape and get bigger and bigger as it goes that way. And did you do logs? Or any logarithm goes the other way, that way. It goes down to minus infinity here and goes up very slowly this way. So getting just a general vague picture of what it's like is useful for making sense of some things. So every time I do it today, I'll tell you what I'm doing. Okay, so I might just put okay, so bisection method. The bisection method is a way of figuring out approximately a solution to an equation without having to actually solve it like we were doing there. It's a way, basically, it can solve anything as long as there isn't a horrifying hole where the function isn't defined in between. So as long as your function's continuous, you can do it. And it's based on this idea, which is called the intermediate value theorem. So the intermediate value theorem says that if you have a continuous function for some interval where x is between a and b, then for every number I shall pick a k between f of a and f of b, there is a c between a and b with f of c equals k. That's the formal maths definition of the intermediate value theorem. So when I say it aloud, I don't normally say all of that. I say that if you have a continuous function and it passes through two numbers, it has to pass through every number in between. So the idea goes that if your function is defined everywhere between here and here, it's allowed to be defined outside of this. And if it passes through this point, and it passes through this point, so that height there is f of a, and that's f of b, then it must pass through every number in between. It might pass through every number in between more than once. It might pass through numbers that aren't in between there, but it will definitely pass through every number between. So every number between here and here, no matter how I draw this function, every height has to be covered. Every height between here and here is covered at least once, no matter how I draw that function. I could draw a perfectly good straight line and that would do it too. I could do something like this and that would do it too. No matter how I drew the function between here and here, if it had to be continuous, which means I'm not allowed to take my pen off the page, it must pass through every height between here and here. That is what the intermediate value theorem says. So this is the value k. That's f of a, that's f of b, and somewhere in the middle there has to be a c, possibly more than one, that produces the number I was thinking of. That's the intermediate value theorem. And it's fairly, makes sense. If you're not allowed to take your pen off the page, you have to cover everything in between. That makes sense. Yep. It doesn't have to be increasing.
But if you put the function of c and b, then there's a value, let's say b is not between c and b anymore, right?
So you're saying there's one here?
Yeah.
But it's still between here and here, though. So you're saying if I had this, every number, what I'm saying is every number between here and here is covered at least once. And they're covered in this bit here. So essentially, it's a good idea what you're doing there. If it goes up from here to here, basically that's saying it has to go up at least sometimes. Even if it comes down sometimes it has to go up in order to cover everything in between. In order to get from here to here, even if it comes down, it has to go up eventually, and that will cover the up bits and the down bits. They're very important questions to ask yourself. If it's increasing, then it's way easier to tell what's going on. But it doesn't have to be increasing, it just has to be continuous. It's allowed to go up and down and up and down and up and up and down and down and down and up and up and up. As long as it gets to here eventually, it has to cross everything in between at least once, possibly twice. In this case, it crossed it 3 times. Okay, so the point of the theorem is that we actually don't know what that function is doing in this zone. We don't know where it crosses this line k. We just know that it does somewhere in between. So what we're going to do is we're going to try and narrow down the zone in which it is very, very small so that we can say, well, we don't know where it is, but it's definitely between 2.01 and 2.02. And that's good enough. That's the idea behind it. And the bisection method is trying to narrow down where a particular answer happens by figuring out what happens on either side. And it's usually used by figuring out what happens when it's equal to 0. So there's a special case. If your function is below 0 here and above 0 here, then somewhere in between it has to cross 0, possibly more than once. If f of a is less than 0 and f of b is more than 0, there is a c between a and b with f of c equals 0. This is the classic one, to make things equal to 0. But no one really cares, you can make it equal to whatever you want. But it just happens most often that you want it to be equal to 0. Okay. So the bisection method comes from this idea. And if we can just continually check whether it goes above and below on a zone, so if I have a function and I know it's below on one side and above on the other, then it definitely crosses the x-axis somewhere in between. And so if I can then say, aha, well, it's below here, then it definitely crosses the x-axis on this side. It might be over here, but we don't know for sure. So if I had a function like this, and I didn't know what happened in here, I would know definitely that it would have to cross the x-axis between here and here. It might still cross the x-axis here, because it might come down then come back up again, but I don't know for sure because all I know is these 3 points. That's the idea behind it. So I'm not sure if it's 0 here, but I'm sure that it's 0 somewhere in here. And this is the idea behind how the bisection method works. And it's easier just to give an example. These are both positive, so I can't be sure if it's 0 in this spot. It might be, but I don't know. But I'm absolutely certain it's 0 somewhere in between here and here, because one's positive and one's negative. And that is a very excellent question you asked to make me clarify how I made that decision. You should always ask your lecturer how decisions are made. Okay. So it's easiest to give an example of using it. I mean, it's technically the bisection algorithm, I think. Now, if I was teaching a computer to do it, I would act slightly differently to doing it myself as a human. So it's just worth noting that, and I'll point that out when we get there. So it's easiest to do the bisection method. Just give me a moment to actually come up with something that has a solution in the zone that I'm thinking of. Okay. Well, that's not an E, that's a 2. To, I don't know, 3 decimal places. Okay, so find a solution to the equation 2 to the power of x equals 5x between x equals 3 and x equals 5 to 3 decimal places. Okay, so at the moment, this doesn't look like I can use the intermediate value theorem for it, because the intermediate value theorem is designed for a single function equal to a single number answer, and what I have is 2 functions equal to each other, so I need to create a function that is equal to an answer that I want at the place where I want it to be. So I can do this. I can create a function which is that, and then x is a solution to 2 to the x equals 5x when f of x comes out to 0. So when this is 0, then 2 to the x is the same as 5x. That'll be 0 when they're equal, and so that's good. So now I've turned it into something where I want f of x to be 0. So I can use the bisection method for that, and I can only use the bisection method if if this function is 0 definitely between 3 and 5. And so what I need to do is start out by calculating what it is at those points. 3 equals 8 minus 15, which is negative 7. And f of 5 is 2 to the 5. Cool, which is plus 7. Nice. Okay. Did not expect that to happen. It's irrelevant that they're the same number. The point is that one of them is negative and one of them is positive. So this is the short negative and plus of the if, negative and positive. Okay. So that's the point. And so what we're going to do is every time we find a zone in which it's negative on one side and positive on the other, we will divide it in half and we'll try again. So I'm going to say it's going to be halfway between these two, which is 4. I didn't actually need to do the average to calculate what halfway between 3 and 5 is. I know that that's 4, but it's good to know that you can do it that way. And then what I'll try is I'll see what happens when it's equal to 4. F of 4 is 2 to the 4 minus 5 times 4, which is 1, which is still positive. Okay, so it's at this point that I would always draw a diagram because it's easier for me to see what's going on here. So what I have here is here at 3, 4 and 5. At 3 it was negative. At 4 it was positive. And at 5 it was positive. Yep. Minus 1? Oh, that's 20. 5 times 4 is 20. Okay, thank you. See, this is why you need to call out. Don't you just wish you had a classroom of fairies to be your mistake fairies in your exam and tell you when you've done something wrong? Negative 4. All right, negative here. Beautiful. Thank you. So this is my diagram. I don't know for certain if it crosses if it's equal to 0 in this zone, but it's definitely 0 in this zone because it goes from negative to positive here. So I'm going to say my second x is going to be halfway between here and here. You can do the 4 plus 5 over 2 if you want, but if it's easier, and it is easier for me in my head to just go, oh, well, that's 4.5. That's how you get halfway between. And then you would just keep trying. And this is where I would get a calculator to tell me what the answer is. Can't use your phone in your exam, but close enough. .13, which is positive. So we were in this zone. So before, because it crosses here, I chose this zone. And now because it crosses here, it goes from negative to positive here, I'll choose this zone. Now it doesn't have to be going up, it can be going down, and that's okay. It can be going from positive down to negative, and that's all right as well. It still crosses in that zone. And so then I would just keep going until I knew what did I say, 3 decimal places? Oh, that's a bit extreme. I really should have chosen more than fewer decimal places than that, because I'm going to have to be doing this for a while now. So x3 would have to be halfway between these two. 4.25, and f of 4.25 is... Most people, when they've been doing this for a while, they stop writing down the actual answer in this bit here and just calculate it. Wow, that changed a lot. Which is negative. So my diagram's looking like this. 4.25, it was negative here, and at 4.5 it was positive there. So that's this zone blown up to be bigger, and it's this bit that I need to look at next. And so I will continue until it doesn't change until in the third decimal place. So in the spirit of making this easier for myself, I'm going to make it 2 decimal places, because I don't want to go all the way to 3. So x4 is now now we're getting to it. Okay, cool. I should have known that, because 3/8 is my favourite fraction, which is what 0.375 is. Okay, and then I would keep going. Still negative. So there's my 4.25, there's my 4.5, here's my 4.375. So it must be in here somewhere. So what I am going to do is there's no point me doing this accurately if I only want the second decimal place. There's no point me going to 4 decimal places if I only want 2 decimal places. So I'm just going to round it off at 3. And I would just keep doing this until I was down to knew what the second decimal place was. And I'm going to stop in a minute because I can't be bothered going much further than this. Wow, continues to be in this zone. Negative here, positive here. Okay, so I'll go halfway between these two. So I do know what the first decimal place is now. It has to be a 4. Because it's more than 4.4 something and it's less than 4.5. So it has to be 4.4 something. So I definitely know that the first decimal place is a 4 now, no matter what it is. And that's what you would do. You would keep going until you were sure what the second decimal place was. So I'm going to just put a note at that. And I might even change my original thing to say 1 decimal place so that I'm done. Wouldn't it be great if you could change your exam question? So actually, I don't like your exam question. I'm going to make it this instead. That'd be great. So I now know that the x is between 4.438 and 4.5. So to 1 decimal place, x is 4.4. I can round it off to 1 decimal place. No matter what number it is between here and here, it'll round. No, it totally won't. That makes me so angry. Damn it, I'm wrong. Because if it goes too close to the 4.5, it'll round off to 4.5, won't it? One more, and then we'll know for sure. Hopefully. Just a second. Four, three, eight. There we go. If I'm very lucky, six, nine there. Still negative. Okay, now I know for sure that it will round off to 4.5, because the place after the 4 is a 6. It'll round up now. Okay, cool. So the x is between 4.469 and 4.5, and so round x to one decimal place, and x will therefore be 4.5, because both of these round off to 4.5 to one decimal place. Right. So the moment, if you're going for a certain number of decimal places, once you get to a point where both ends round off to the same thing, then you know you can stop. If you go into 3 decimal places, I would have to go a lot further. The point of it is, I was able to only choose 3 decimal places here because that's all I would only have gone to 2 decimal places if I was doing the 1 decimal place. So you only need 1 more decimal place than the decimal places you're going for. So if you're going for 3 decimal places, I'd only mark my numbers as 4 decimal places wrong, for 4 decimal places long. So if when I got this, I got something that had 4392114, there's no point using those last ones because I only want it to be accurate to 1 decimal place anyway. So just useful. But if you're using Excel, then just do whatever you want and it'll do as many decimal places as it has, and that's fine. Okay, that's the bisection method. So all I want to say is you can round off as you go. It's approximate anyway. Just keep going until you know how many decimal places you need. So the only thing I could ask, I could imagine someone asking you saying, well, how many steps are you going to need to get to the accuracy you want? I don't know if they ask that sort of question, but you could imagine that. To get to 3 decimal places of accuracy, that would be a question that you could ask. And I guess the idea is every time you divide the interval by 2, you get the zone down a bit smaller. And if you want it to round off to 3 decimal place accuracy, 3 decimal place accuracy means that you're going to have, for example, something like if you got down to here, for example, and you knew it was between here and here, then you would know that to 3 decimal places it is definitely 4.388. So if you wanted to get it down to definitely 3 decimal place accuracy, you need the width of this interval to be 0.0005. That's what we need to get 3 decimal places of accuracy. 4 decimal places of accuracy would be 0.00005. You need basically the same number of zeros here as the decimal places. And so, if I needed to do that, well, I started with an interval that was 1 wide. No, 2 wide. So I started with 3 to 5, which is 2 wide. I need to keep dividing. Every time I do a step, I'll divide that interval in half. So I'm going to need to keep dividing that in half until I get under 0.005. And then I'll know. So I need to go to, damn it, to bisect until the width is 0.0005. No, not Siri, 0. Sorry. You should see what it does when I'm trying to read Harry Potter to my daughter. Sirius, not Siri. Okay. So we need to know when we started with 2 and we divide by 2 however many times. If you divide by 2 once, it'll be dividing by 2. Dividing by 2 twice would be 2 to the power of n. 2 squared, dividing by 2 3 times would be 2 cubed. We need this to come out to be less than 0.005. So we need to choose the right n. And the quickest way is probably to just keep putting in numbers until it works. Let me just see. 2 divided by 15. 15's too far. 11, not quite far enough. 12, okay, that does it. So I just kept trying different answers for n until it got small enough. So 2 over 2 to the 12 was 0.00048. So need 12 steps. I don't know if they'll ask that question, but it's useful to be able to think about it. Did they do Newton's method in this course? Good, okay, won't talk about that then. Yep. This bit? Okay. So that was the bisection method. For me, I find drawing that diagram each time really useful. I used to draw one big diagram and keep cutting it in half, and then it would get really annoying and all close together if I did it too many times. In most exams, they try and arrange it so it'll only take 2 or 3 steps, because otherwise it just takes too long. Or they'll just literally say, do it 3 steps. What's the answer? Okay, cool. Well, that answers that one. So out of the things that are written on the board, what preference do you have, people? Simplex? Let's go. All right, I'm going to go to the notes. So these are the outline notes that were on my uni, and I'm just going to have a quick scan to see what it says and try and make sense of what it is. So this is the only maths course that the School of Maths teaches that has the Simplex algorithm in it. Like bisection methods in both is in Maths 1M and Intro to Financial Maths and Maths 1B, so I know that one quite well. This one is only in this course, and this course only happens once a year, so I don't know it quite as well as the other things. So I'm just going to have a look at what this says. The simplex algorithm is similar to the algebraic method described in the previous section, but it's more efficient because we do not need to find all vertices of the feasible region. Okay, so the method before was like you had to do all the row operations until you put all of the, and you put slack variables in, and you had to do all of the row operations until you got all of the basic variables, and then you had to sub them all into the thing and see which ones of them, and then you'd figure whichever one was the smallest is where the minimum was, and whichever one was the maximum is where the maximum was. Okay, cool. Good to know. So this one this simplex algorithm is supposed to avoid having to calculate it all of the vertices. So it's supposedly faster, in inverted commas. So because it's faster, that means it's probably more complicated. So things that get to the answer, directly to the answer, usually are a little more difficult to do along the way. Okay, so let's see. We were given an optimization problem in standard form. So we maximize an objective function, f of, oh, that's a bold x. So that bold x means it's a vector, so that must be the coordinates x1 up to xn. Subject to the constraints A, where I'm presuming A is that's a matrix, yep. X in bold is a vector, but it would have to be a column vector if it was on this side of the matrix. You can't put row vectors on the right-hand side of a matrix. Is less than or equal to B, and B is also a vector. And X has to be greater than or equal to 0. Just a second, I'm going to write that down properly, just a sec. So this is saying, was this C? Yeah. C1, X1, Xn, and then we have AX equals okay, so when I write a vector that's in bold in the notes, I put an underline in it, in my handwritten notes, so that I can tell that the person who was writing it in the typed notes put it in bold. So there's got to be a better way of doing that. I just want to have an example of what that looks like. So it would have to be something like f is like, 3x minus 5. Something like that. That would be an example. And then the ax is less than or equal to b would totally be... So if I did matrix times column, that's normally the coefficients of a set of equations. That's normally what this is. And so I reckon it's going to be something like, I reckon this is what that means. This is the sort of thing that they're doing. Whoop, less than. Is that greater than? Sorry, this was a greater than to begin with. So that's what the book said, and I reckon this is what that means. So this bit here, that's this. And this bit here, that's this, and this bit here, that's here. And the way that this makes this is that I think this is the same as 2, 0, 8, 0, 1, minus 5, 1, 1, 1. That's the matrix which comes from these coefficients here. Like that. So we have 2 of x1, none of x2, and 8 of x3. That's this part of the equation. That's what this bit here is. 0 of x1, 0 of x1, and 1 of x2, and minus 5 of x3. That row and this column together make that bit. And then 1 of x1, 1 of x2, 1 of x3, that row and that column make this bit. Sorry? 1 of x2, where? Second row. Yep. There's no x2s there? Sorry, second... Yep, it's all good. It can be very confusing to read these when you haven't written it yourself. And even I have trouble. So basically, this is the matrix. This is A here. and this is the x, and this is the b. So I don't think you I don't think you have to be able to turn this into the thing with the matrix. I don't think that's actually necessary. It's just their way, it might be, but it's just their way of writing down in short form what this thing is like. Okay, good. Now I understand what that is. So this is the sort of thing that would happen when they do the classic is cereal, I think, in the book, with, you know, Nutty Crunch, and this one, it's got this many almonds and this many things, and yeah, so much time for your factory and that sort of thing, and those sorts of problems. That's the sort of problems we're working on. Okay, good. Okay, so cool. So somehow we turn all this information into a thing that we perform this simplex algorithm on. Now I know that the word simplex means the shape that happens when you intersect a whole lot of planes. So when I, in 3D, intersect three planes, I might get this pyramid shape, and that's a simplex. So that's the idea that I'm aware of. So it's designed to be thinking about the same thing that your normal convex set thing is with the vertices, but without actually going through all of those things. So the computer says that we set up the Simplex Tableau, we introduce m slack variables so that the constraints become ax equals b for a little bit bigger matrix, and a new variable z, which is the current value of f of x. Okay, sure, right. So I'm just going to run through it with this example and see what happens. So basically it looks like each inequality gets an extra variable. Oh. So the first one, I really would prefer not to write them as x, 4, 5 and 6, but that's what your lecturer has called them. But I would normally call them S, 1, 2 and 3, S for slack variable, because it helps me keep track of which one is which. Is that what the lecturer does? Some of the tutors do? Are you okay with me doing that? Okay, good. So slack variable number 1 to go with equation number 1, and slack variable number 2 to go with equation number 2, and slack variable number 3 to go with equation number 3. So the idea of this is that the 2x1 plus 8x3 might come out to like 6, in which case the S1 would be 4 to make up the extra to get to equal to 10. So it's called the slack variable because it picks up the slack. This might only come out to 6, so we need an extra 4 to make it up to 10. And so if we just randomly picked a set of coordinates for x1, x2, x3, it may turn out that the 2x1 plus 8x3 came out to be more than 10, and the only way to make it be equal to 10 would be to take something off. And so we really don't want those s's to be negative, because that means that it doesn't actually satisfy the constraints. Okay, cool, good with that. So we've got that. And then what we're going to do is we're going to have f is called z. Okay. Okay? Sure. Fine. That's a Z with a cross through it, so you can tell it's not a 2. All right. And the way that the lecturer writes that is that you do this. Like that. So this isn't a slack variable. This is just giving a letter to the outcome of the function. So this thing here produced that. According to the notes, that's what the notes say, just here. Okay. And then you write all this in this great big tableau. Sure. All right, I can play this game. So you have x1 and x2 and x3 and s1 and s2 and s3 and z. and we have 2x1, no x2s and 8 x3s and 1 s1 and none of the others equals, and no z's equals 10. 1 no x1s and 1 x2 and minus 5, and that's equal to 8. 1, 1, 1, no s1s, no s2s, 1 s3, no z's, and that equal to 6. And then finally minus 3x1 and 5x2 and minus 8x3 and none of any of these and 1z equals 0. A whole lot of stuff going on there. Okay, cool. So technically you could probably, if you were paying attention very carefully, skip straight from here to here. Like if you were being very careful, you could go straight, here we go, let's put them sideways. You could go straight from here to here if you were paying attention. Yep?
In the fourth row where you've got the C, is it supposed to be a negative C? Just above the lines equations. Just one above that.
No. Because, well, I'm just covering what the notes say, and the notes have a plus Z.
Oh, well, I thought the line above that would be a negative C. For it to go positive Z above the
I pulled a Swiftie. I moved all this over there. And then it was 0 equals that. So technically it's this. Like that. Yeah, I moved all this over there. Yeah. Yep.
If you skip that slack variable part, and went from the final matrix to the
Yep. I don't know. So I don't know if you would lose marks or not. To be honest, it probably doesn't matter. I would probably, only having learned this today, I mean, I'm sure I did this a year ago, but only having learned this today, I wouldn't be able to do it directly myself. But I'm pretty sure that this is all set up so that you don't need to technically add the slack variables at all. But you do need to put this part of the matrix in. Yeah, I reckon it'll be okay. You do need to absolutely make sure, no matter which way you do it, that all of these are less than or equal to. If any of them are greater than, you have to multiply everything by a negative to make them flip the other way. So I think some people add a slack variable. If this was a greater than 6, then they'd put a minus S3. And so if you add your slack variables that way, then you have to be really careful. But if you always make it less than or equal to here before you do anything, then you can probably skip straight to there. Yeah. And I reckon the people marking it won't care. Because they're not really looking at this part, they're probably just looking at this part. I can't be absolutely certain, but I know I as a marker wouldn't want to have to check if these slack variables were right. So, yeah. But I can't be sure, because I'm not part of the School of Maths. I'm Maths Learning Centre, which is central, belong to the whole uni. So some of the people who work in the Maths Learning Centre also work for the School of Maths. But when they're in the Maths Learning Centre, they're not supposed to give you that sort of information. Okay. So then let's see, what does it say? So I can set it up. And then it says, the last row of the Simplex Tableau describes the objective function. Sure. The optimality test is, does the objective row contain no negative numbers to the left of the vertical line? So we don't want any this is the vertical line here. So this says that if there's no negative numbers over here, then we have found the optimal solution and the simplex algorithm is complete. Okay, cool. Which is not, because I've got some negative numbers. Okay. The optimal solution is described there by the basic solution of the Simplex Tableau. Okay. Find the pivot column, find the most negative number in the objective row, and then that's the pivot column. Okay. This is the most negative number here. That's the pivot column, apparently. It's the biggest negative number in that row. Okay. The column containing, it's called the pivot column. Find ratios by dividing each element in the rightmost column by the corresponding element in the pivot column. The pivot row has the smallest non-negative ratio. Okay. Oops, sorry. So my ratios are this divided by that. Okay. So 10 divided by 8, 1.25. 8 divided by negative 5. It probably doesn't matter what that is because we only want the positive ones. Smallest non-negative ratio. Okay, well we don't care, but it's negative. And 6 divided by 1, whoops, sorry, is 6. So that's the smallest one there. Okay. If there is no such row, then the simplex algorithm stops because there's no optimal solution. Okay, cool. So we have a row. So that's my smallest non-negative there. And so that's the one I'm interested in there. Okay, good. This is fun. You really wouldn't want to be doing this in your exam, never having seen it before and just reading off your cheat sheet, right? That would be really bad. Okay. Perform row operations. Perform row operations so that the element in the simplex tableau, which is in both the pivot row and the pivot column, that would be that 8 there that I found, is a 1, and the other elements in the pivot column are 0. Then return to step 2, which was choosing a pivot, applying the optimality test. Okay, cool. So I can do row operations. I'm good at them. So our goal is to make this a 1 and everything else a 0. Including this one? Oh yes, because I have to change that row or I'm not going to be able to do that optimality test that I've just been asked about. Okay. So traditionally you would normally make a 1 here by dividing by that number. So okay, didn't change this row, didn't change this row, didn't change this row yet. Oh, I can make a 0 now though. Yes, I think I can make a 0 now by just adding them together. There's no reason I can't make the 0 before I make the 1. Yes, I'm going to do that first, if that's okay. So I'm going to do row 1 is an 1/8 of row 1, and before I do that, I'm going to do row 4 is row 4 plus row 1. So row 4 is row 4 plus row 1. So that's row 1 there. So minus 3 plus 2 is negative 1. 0 plus 5 is still 5. 8 plus 8 is 0. 1 plus that is a 1. This plus that is 0. This plus that is 0. This plus that is still 1. Damn it. And 10 plus 0 is 10. Okay, and then I divided this one by 8. 2 eighths is a quarter. That's a 1. Okay. Okay, cool. So that was I'm still not there. Let me just check. I needed a 1 here and a zeros here. So I'm going to need to do row 2 is row 2 plus 5 of row 1, and row 3 is row 3 minus row 1. Okay, I didn't change row 1. And this plus 5 of that, 1.25. This plus 5 of that is still 1. This plus 5 of that is 0, because that was the point. 5, 8. Oh, that'd be 6. 1 plus 5 of that. This plus 5 of that. And this minus that is 0.75, 1, 0. Six take 1 is 5, so 4.75. Okay. I have now gotten to the stage I was supposed to get to of getting a pivot column, and so now I start again. So let me just see if I've got my starting again rule right. I have a look to see if all of these are positive yet, which they aren't. And so if they're all positive, I would just stop, and that would be my answer. That's the idea, like none of them are negative. Let me just go back. No negative, no. Okay, so if none of them were negative, I would have the answer. And if any of them are negative, I choose the biggest negative answer. And that's my pivot column, so that's my pivot column there. And then I do my ratios. So 1.25 divided by 0.25 is 5. 14.25 divided by 1.25. I don't want to do that one in my head. It's bigger than 5 though. Whatever it is, it's more than 5. And 0.75 divided by 4.75 is less than 1. Okay, so I needed to choose the smallest non-negative answer, which is this one. And so that's the one I want there. Okay, doing well. And so then I will do my row operations to get to wherever I need to get to. I need to make that a 1 and everything else 0. Yeah. All right, here we go. I think dividing by 1 is a good idea. Dividing by the 0.75 as the first step is a good one. So I'm just copying out the matrix, the rows that I didn't change. I'm thinking in an exam they probably only want you to maybe choose which position it is and not do any row operations of your own, possibly. Or you could imagine them getting you to do just 2 row operations or something. Or say, what is the next row operation you would do? Instead of getting you to rewrite the matrix every time, because you only got 2 hours. Yeah, well, then they would give you one that was smaller than this one. It wouldn't have 3 variables in it and 3 equations, I wouldn't say. So this divided by 0.75 is 1. Oh, that'd be 4/3. Well, that's 5/4 divided, so that's 5/3. Oh, come on. Of course it's 19/3. Okay. I just did it in fractions because I didn't follow. Yep.
For the last ratio, should that be like 4.75 divided by...
Oh, I did it round the wrong way. You're totally right.
Because maybe 5 could be the smallest.
You're right. I did that wrong way. It's this divided by that, isn't it? Oh, crap. Just all that for nothing. .75 divided by 0.75 is more than 5, right?
Yes, 6.2 something.
And so it's actually this one. Didn't we just do that one? We're going around in circles, people. That's going to destroy the zeros we just made here. Oh well.
Isn't it because we don't care about what happens on the left-hand side? We're trying to play with the numbers move across to the right.
Ah, cool. So it's not this one at all. It's that one. Okay. So these are all more than 5. We choose the smallest one. We choose 5. So is that what happens? It all moves across now, does it?
Yes. So it should come out to be the inverse. So, not the inverse, sorry. Identity, sorry.
That would make sense.
Yeah.
Yes, because it would tell you what each of the variables was. Okay. That's a half now, isn't it? That's a 1. Wow, so many places to be wrong. Okay. So I think by the time we've done this, everything will be positive by then. Because we don't have any negative numbers up here, so when we add them down here to get rid of that 1, it'll all be positive by that point. So there's only one more step to go. Good. Okay. So, is that okay? So conceivably, I could just know that the answer is 15 for what the maximum is. Because I'm going to go row 3, 4 plus row 1, that'll put me at 15 in this spot. So that's the answer, that the maximum is 15. I'll just see what happens if that's okay. I'm just going to do it properly. So we're still focusing on this column and this position. So row 2 minus 1 is row 2 minus 1.25 of row 2 So this would be 0, 1, minus 5. Zero. Cool. Well, that's going back to where we were. How interesting. Cool. So 0, 1. 0.75. This is going to be even more negative. Zero point 4.75 1. And also row 4 is row 4 plus row 1, which is 0, 5, 4, 1.5, 0, 0, 1, 15. Okay. So that says, so now I stop because there's no negative numbers down there. Okay, so that says the maximum is 15. This finds maximums, doesn't it? Sorry? Yep. But I think if you want to find a minimum, you have to put the minuses in different spots. Pretty sure it finds a maximum. Optimisation of where positive is best. So.
The optimisation maximum would be
Yeah.
Z score should be maximum.
Yeah. But if I had wanted to find a minimum, then I would have made sure this had been a negative one instead, and I think it would have worked. Just minus everything. Find the maximum of the negative is the same as finding the minimum of the original. Anyway, so this is saying that that's the maximum there, 15. Does it tell me when that happens? Okay. So this is saying that 5 and 4x1s. So this is the confusing bit here for me, because I haven't been taught how to read the answer at the end. Definitely know that this was the value of, well no, just a second, that's not what z is at all, is it? Is the z, that's 1, that's the maximum, not the 15? This is a bit I'm not sure on. Sorry? Yeah, well, where did that come from? So that came from here, where we called it was z. Z was what was all of this was equal to. And so this thing, this calculation of z minus all of this stuff came out to 0. So this is now telling us that 5x1s and 4x2s and 1.5 s1s and z is 15. And what does that tell me? I don't know what that tells me. And I have to, it's not clear in here, there's an example somewhere in someone's notes where we're telling you how to read off the answer. This is where I would Google it.
In this video, we'll take a look at 4 different examples of a tableau, and then we'll be asked the question, based upon the tableau, does a maximum exist? By determining the basic or act. So first, notice how the maximum of p, our objective function, equals 225. So that's the second question. The maximum exists. What is it? It's p equals 225.
Okay.
Analyzing the table, we also know that x sub 1 equals 425 and x sub 2 equals 450.
Okay, so we've got some setting things to 0.
Yeah, so find the basic variables. Find the basic variables. So we know what the basic variable is at the bottom. So we know there's no x1s. x2 is equal to 5. x3 is equal to 4. And then we know that 1z will be 15.
Okay. So that really is the value of z?
Yeah, and then we know we exclude the slack variables.
So just a second. I think I can reason this out to make sense of it. In the old algorithm, we had to set various of the variables to be 0 in order to figure out, look at that. In the old algorithm, we had to set various variables equal to 0 in order to find the value of the maximum. Like the vertices happened when the slack variables, or possibly the original variables were equal to 0. And what I used to do is look for a little identity matrix and it would tell me what those variables were. So I think if I see there's an identity matrix here, here, and here, which I think is telling me that if I cover up this bit, it tells me that x1 is 5, x2 is 0, x3 equals 0, and z is 15. So I've found a little identity matrix, a 4x4 identity, and that tells me what everything is. And that's what I need to do. And you were looking at that just then with setting things equal to 0. Is that what you were looking at? Yeah. So basically anything in here that... Yeah. So anything in that bottom row that isn't 0, I set it to 0. And it doesn't tell me what those variables are. Those variables are 0. So sorry, and that's why the z is 15. Yes, okay. Good. And you make all of these 0, and so the z is 15. Okay, so the maximum value is f, which is z, which is 15, and it occurs when x1 is 5 and x2 is 0 and x3 is 0. Like that, because these two variables don't appear to the solution. So any of these ones have to be 0. So these ones are all 0. And then the other ones I can figure out what they are from what they line up with. And that's how I figured out these answers here. And I don't need to know what the slack variables are because I only made them to create the problem, to help me solve the problem.
But I think you still do write down that x equals, x 5 equals 8, and then x 6 equals 1.
Yeah, because you go from the end column, so.
But technically, if we were really solving this problem for ourselves, we wouldn't care what they were. Because those are just, I mean, it's useful information. If these equations originally represented how many of our various bits and pieces we had used or not, we'd know that we had 8, you know, if one of them was the amount of time we could use the oven for baking things, we'd know we had 8 hours to go or something like that. All right, well, I have never understood the simplex method before. I reckon I could do this now, if I practiced another one maybe. Yeah, so I'm feeling better. I needed to see a whole one in action to make sure I knew what was going on. Cool. So this gets around what we used to do with the slack variables and the vertices by choosing specifically which spots we want to do the pivots on. Whereas in the other method, we did the pivots in all possible spots. Whereas this one, we do pivots in just these spots, and then it just tells us the answer at the end. Clever. That's some clever stuff, I have to say. So that real key is that ratio bit there, of making sure you get that right, to make sure you choose the right spot. And even if it does look like you're undoing what you just did, that's okay. Good. The worst thing is when the other Maths Learning Centre lecturer, Nicholas, talks about Jamie Oliver being such a good TV cook because he tells you what things should look like when you're done and when you're on the right track. He says, oh, well, if you're doing this right, then it should curdle or not curdle. If you're doing this right, it should start looking like this. So you can tell when you're on the right track. So it's nice for me, and hopefully for you, to know it is okay to look like you're undoing the zeros you made before. So it's good to know when you're on the right track. And it was good that you should progressively have fewer and fewer negatives in this bottom row as you move through the algorithm. Because each time there's a negative, you should be basically eventually replacing it with 0. Yeah, got it. Nice. So if I were to write a thing for myself for doing on a piece of paper that I was allowed to take into the exam, I would try and write something that helped me remember what to do at each of those steps. I would probably write it in a loop and go, well, if there's any negatives, if there's no negatives, stop. If there's any negatives, find the biggest one, and then do this, and then go do this, and then go back to the beginning. And I would not forget to include the bit of how to interpret the end, which doesn't seem to be written explicitly in the notes anywhere. So, yeah. Cool. All right, well, I was supposed to finish at 3, but if there was something simpler than half an hour long, I could talk about it if you wanted me to talk about something, because the recording is going to go for another half an hour. Can't go through the whole sample test, but that guy's gone anyway. So, anything that you saw, a question that you seen in the sample test that you were not sure about, or do you want me to talk about finding determinants of things? Don't even know what the Hill cipher is actually. I'd have to look that up. Presumably there's I seem to remember there's a matrix that you have to do the inverse of. So the key there is finding the inverse of a matrix. Really? Maybe I should just talk about that. I'm just going to check that I'm doing things in the way that your lecturer prefers. So was that at the beginning of the algebra?
Yeah, that was the matrix.
Yeah.
That was pretty early on, so it was
determinants. Okay, and then inverses. Yep, I don't care about the Hill cipher, I just want to do determinants and Latin stuff. Okay, so it doesn't look like 3 by 3 matrices are in the plan, in the notes per se, in the lecture notes per se, so much. Okay, so well, I'm just going to talk about it. Matrices are a useful way of doing all sorts of crap, and the 2 by 2 matrix would tend to be this flavour, something like that, for example. It would be really useful to have things that were not whole numbers. They don't have to be whole numbers. It's classic. Mathematicians tend to be not particularly comfortable with writing numbers as decimals because it makes them feel like something's been rounded off, which makes them uncomfortable. So you should be able to do things with fractions if you want. You know, random things, that's what a matrix is. The point is that your matrix is usually when we're using matrices, at least in this course, your matrix is representing the coefficients of a set of equations. And it's usually being used for something like this. You know, something like that, and these coefficients went together to produce this matrix. That's what you normally use them for. And so this would turn into that matrix xy like that. So the reason you might want an inverse is to believe at least that it was possible to solve this. So if this is sort of similar to the sorts of equations that we're used to solving with plain numbers, where you had like 4x equals 20, and you would divide by the 4. But we have this chunk of numbers times this pair of numbers equals this pair of numbers, and we're like something that does the same job as dividing by 4 in an ordinary equation as it does for this, but somehow, in inverted commas, divide by this matrix. But there is no such thing as division for matrices because it's so complicated doing this multiplication. But what we do have is a thing called an inverse. That many matrices, most random matrices that you would care to come up with, will have a matrix you can multiply in this spot here, so that will come out to the identity, and the identity multiplied by anything doesn't do anything. So that's the goal. So what we want is to be able to put something here just like with any equation, you can multiply both sides by something. We want to put something in this position here so that this bit becomes the identity which would mean that xy is whatever this answer is. So whatever this times that is, it comes out to this, and then xy comes out to that. That's the goal. That's what we want. And this thing here is called the inverse of that matrix. I'm going to put that in a little. This is the inverse of this. And just like inverse functions, we write it as to the power of -1, we do it with inverse matrices too, because that's our classic way of doing things that undo other stuff. So if this was A, then A inverse, well, that's the inverse that we want. And there is a formula for finding the inverse for a 2 by 2 matrix. For 3 by 3, it's much harder. There's a formula for finding the inverse of a 2 by 2 matrix, and it is switch these two, minus those two, and divide by the determinant. So you'll switch those two numbers, you'll minus these numbers, and you'll divide by the determinant of the matrix. Yeah. So I'll just put det A there. So the reason we would like to know what the determinant is because it helps us to do this. But also, if that determinant is the number 0, we're not going to be able to calculate this because it would require us to divide by 0. And it's not going to be possible. Where det A is calculated by doing those two multiplied minus those two multiplied. Which is whatever the hell it is. (1.25) times 5.2, whoops, minus 8.6 times 3. So in my head, just so that you've got what's in my head. So you'll notice that the inverse, if you've got nice big numbers, your inverse will be divided by that rather big number, and it will tend to have small numbers in it, because we've literally got 5.2 divided by 32.3, which is a nice small number. In the same way that if I had the number 4, its inverse would be a quarter. And so if you have something that's mainly big numbers, then the determinant will be big, and your matrix tends to be made of small numbers to make them go away. And vice versa. So I just want to show you where I was going with that. So the inverse, we switched these two, and we minused these two, and then we also calculated this to get the determinant. Well, that was a +3 before. And then we also calculated this product and this product, and we did that minus that. That's the determinant. It's very hard to write that down on paper so that it makes sense, but I can see the picture in my head. So this is the picture that's in my head. So that's for 2 by 2s. It's way, way harder for everything else. The bigger it gets, the worse it becomes. And it's probable that in applications of quantitative methods in finance, the second semester version of this course, you'll learn how to do the other ones. Determinants of 3 by 3s are usually done by building them out of determinants of 2 by 2 matrices that live inside the 3 by 3 matrix. And determinants of 4 by 4s, you build them out of 3 by 3s that are inside the 4 by 4, and those are each built out of 2 by 2s that are inside the 3 by 3. And if you're good at row operations, you can actually keep track of what row operations do to determinants, and that can be a useful way of doing it as well. And actually, row operations can tell you what inverses are, because that's fun too. So, but you didn't have any of that as far as I can tell. For some reason they've told you about elementary matrices, but I don't quite understand why they've told you that. For no good reason that I can see, other than elementary matrices prove that inverses exist. It's like in the mathematics proofs that go behind it. That's probably enough to talk about, unless people want to keep asking any questions they have. So the Hill cipher, I think, is done by turning your letters into numbers and multiplying them by a matrix. So to undo it, you would have to find the inverse of the matrix. And that's basically the deal. It's good practice to do this with things that aren't whole numbers, because people get this whole number sort of addiction, and you start to feel like you don't know what to do if you don't see whole numbers. So it's good practice to do them with fractions and decimals so that you can make sure that you don't freak out when you don't see them. Okay? Cool. I had to be next to a building site. They weren't doing this last week. Okay. Anything else you wanted me to talk about?
Yeah, just one.
Yep.
The formula used.
Where am I looking? I can't see. Oh, okay.
The formula used for solving a geometric series.
Yep.
Can you just show how we arrived at that formula? Just kind of useful. Like, I understand how it works and all, but
So does your lecturer use this sort of symbols?
no, he doesn't, but you can.
He just says something like this, where you have like
Is equal to S of n divided the sum of the series.
that sort of thing.
Yeah, sure.
That's what you would see as a geometric series.
Yeah.
Or something like Sn is that sort of thing. Okay. So are you asking for the formula that adds it up to the point n, or the one that adds it up forever?
The one that adds everything up
From
from
to the end,
N1 to Nn.
but it stops somewhere,
Yep.
as opposed to adding up a 1.5 and a 16th and a 32nd and do that forever and see what the answer comes to. Okay, good, just making sure. So something like that. Okay, good, just making sure. And it might not start at 1, it might start at like 5, and then you have like, and so I just want one more. And you might have something like, something like that. That sort of thing. Cool, just making sure I've got the right thing. Okay, so it's called geometric because you keep multiplying by things, and the idea is that you make lines and squares and cubes, and that's the geometry. Okay, I'm just going to look it up. I'll make that up. Okay, so that I can do. So I think the formula that you would have would go like what?
Sn is equal to N1, and then multiplied by 1 minus Rn, r to the power n, divided by 1 minus r. No, not the whole thing divided, so just the 1 minus Rn. You're not dividing the N1 as well.
Doesn't really matter. Comes out the same answer, so that's all right. Like that?
Yeah.
And this N1 is that first one?
Yes, correct.
Okay. Cool. All right. I would normally call that A. That's all good. Right. I can do that. So we have something like N1 and N1R and N1R squared. Oh, I don't like using n's for both of those. Can I use an A? Okay, so the idea is that your sequence is made of each term is r times the one before. Okay. Cool. All right. Nothing up my sleeves. You sure this isn't an n plus 1?
It's n plus 1.
Do you reckon this is an n minus 1 here? I reckon it is.
Yeah, it is n minus 1 there, but...
Because this is term number n, right?
Yeah, so you want to multiply by that one term just before that.
Okay, yep. So this is term number n because you started with no n r's, and then you had one r in the second position and two r's in the third position and n minus 1 r's in the nth position. Good. Okay, so that's the first thing that we have to be able to notice, is that term number n has n minus 1 lots of r. Okay, so if we go to the next one, that one, that's the next one. So we had the one we had before, and then we added on the next number that we would have had. So if we got up to 5 times 3 to the 7, we're going to see what would have happened if we, this would be S7 here, right? We're going to see what would have happened if we had plus 5 times 3 to the 8th as well. We're going to go to the next one that we would have had after the one that we're currently up to. That's what we're going to do. All right? Am I doing a bad job here? Yes, because I think I'm not sure. I'm just making this up as I go along and trying to remember it. So that's definitely true. The extra bit to get to the next one after the one I'm up to is a times r to the n. Maybe that's not what I wanted. Ooh, this is better. Oh, look at this. Look, all of these have an R in them. So I can do this. Move the R from that one. That's a minus 1 there. Damn it, A1 R to the n minus 1. So I divide this one by R and this one by, all these by R, and I get that. They've all got an R in them. And I can pull that R out. And this, that was Sn. So Sn plus 1 is the same as A1 plus R lots of Sn plus 1, n of Sn. Right, that was a magic trick. Okay, well my other magic trick was the one that I was going to do before. That Sn plus 1 is also Sn plus AR out of the n. So look, this bit is Sn plus a bit to get to the next one. And this, there's two ways of writing Sn plus 1. So, let me just think about this. To get from the current sum that I've got to the next one way is to multiply everything I have so far by r and add the first one on, which is this one here. The other way is to just add the next term, a1 plus r to the n. They're both ways. So I'm going to do this with proper numbers in a second just to show you what's going on. Okay, so since these are equal, they must be equal to each other. A1 okay. I wrote that the wrong way around. It would have been better to do it this way. Like that. I'm going to have Sn minus r lots of Sn, put that over there, and A1 minus A1 times r to the n over there. These both have an Sn, which goes like that, and these both have an A1, and now I will divide by 1 minus r. Ta-da! So, I just want to do it with a proper one, with just one that we know what it is. So S8 would be 5 plus 5 times 3. In fact, I'm just going to do it really small so we can actually see them all. Just so we can see them all there. Let's just go up to 4. That's only S. Yep, that's a 3 here, sorry. So that's S4. It goes up to, it has 4 terms, 1, 2, 3, 4. And S5 would have that. And so this S5 has 2 ways of being made. That is 3 lots of S4, because everything in S4 has been multiplied by 3. But on the other hand, S5 that bit is S4 as well. And so I have 2 equations. These things have to be the same as each other. And so I can use those 2 equations to figure out what S4 has to be. Yeah, very, very slick to go, well, let's go to the next one after the one that we're up to and see if we can do something with that. Very clever to go outside the zone that you're in to figure out the one that you're up to. Cool. Well, let's do it 6 minutes. You were going to ask a question.
Yeah, it's like a long time ago back to the example. So if you want to find what x and y are, you just multiply, I think you can multiply that by the inverse.
Yep.
Okay.
So if you had this, you would multiply by the inverse here, and that would tell you the answer. Yep. Cool.
So regarding the Leon's model,
Okay.
you know the formula x minus ax equals d? I just had a question. What did each of the variables actually represent?
It's an E, isn't it? And an IEF? Okay, so that D is supposed to be demand, in inverted commas. And I believe it's the amount of demand that you could actually achieve, that you could actually meet. So if something external to your system demanded these amounts of each product, then you would be able to meet that demand. This is the biggest demand you could possibly meet. And this is the amount of product you produce. The actual amount of product you actually produce. And this is the amount of product you need to make the product that you produce. Resources, if you like. These are the resources produced, but the amount of to make X amounts of products. So when you have the A, if you wanted to produce 1 of this and 2 of this and 3 of this, you know, if you wanted to produce 1, 2, 3 for your x, then you would need AX, which would be whatever it is. And maybe the AX would turn out to 5, 8 and 6 or something like that. So maybe you want to produce x equals this, then you would need this much to produce that many. Which means that the leftover is what you would be able to give to an external thing. And the idea behind it is that you're constantly using and producing these things. Like the Leontief system is that you have things inside your system that your system makes, and you use those things to make the things that you're making. So you have, you know, gold and sheep and whatever, and you need the sheep to feed the workers to dig the gold, and so you need, and the sheep and the gold, you pay the workers gold, and like all of these things, the amount of sheep you have affects how many sheep you can produce, and the amount of sheep you have affects how much gold you can produce, and vice versa. So the amount of stuff that you produce is constantly being fed back into the system to produce more, but then you use that to feed back into the system. And so if you have this much stuff, that's what you want to produce, then this is how much stuff you're going to need to produce it.
So produce x is the first variable x.
Yep. And then the AX is how much you need to make x. And so in this case, the demand is this is how much leftover stuff we don't need to make the next cycle of things. So if we make these things, we need this stuff to make the next lot of those, and so this is left over to give to somebody else. Yeah. This is an open model. In a closed model, you never give it to anybody else, and so the amount of stuff that you produce at the moment is exactly the amount of stuff you need to make the next amount of stuff. And so this D is 0. Yeah. Yeah. There's no leftovers because there's nobody outside to pay. You're self-sustaining.
So you're going to produce exactly what you need.
Yeah, that's right. I find it easier to think in terms of cycles, but it's all happening simultaneously because it's an economy. There's lots of stuff going on all the time. But we think about it I think about it in cycles. It makes it easier for me. If I make this much, then this much goes in to make another lot of the 10, 20, 30. And I can give the 15, 12, 24 away because I don't need it to make the 10, 20, 30. Yeah.
If you were to remove A in that equation,
The A?
would x and x be the same variables?
Yes, they are literally the same number.
Okay.
Same numbers. Yep. I'm just checking the time because I've only got a minute to go, so anything I say after that isn't on the recording. So yeah, these x's literally are the same thing. And that's why you can pull them out to get an I minus A times x. Because your assumption is that because the system's running continuously, the amount of stuff that you're always producing the same amount of stuff, and therefore you always need the same amount of stuff. And you figure out how much you need based on what you've got. Yeah. It took me years to figure that one out.
Right. So typically a question would ask, how much demand would you need given A? Is that what it would
You're normally given the x.
Okay.
Or no, actually normally you're given the A and the D and you're told to find out what the x is. Because you would normally go, okay, and then if I multiply by the inverse of this,